Hey everyone and welcome back to PrepFusion. I'm Anish and today we will be starting the lecture 5 of Bode plots. So in this lecture what we will study? We study the Bode plots of repeated poles and zeros and quotients of Bode plots basically. And like this the Bode plot section will be ending and we'll start a new topic in the Bode plot itself. Okay. But before that we had a question like that I gave you in the previous lecture. We solved like how to plot the Bode plot step by step methods we solved, right? But we still solve it slowly. But after this we'll solve it very fast. Okay, but here this question was still left. We had repeated real poles. How to plot the Bode plot for this? I haven't taught you anything about repeated poles or something like what happens to the slope, what happens to other things. So first I will do one thing. I will solve this question, but first let's solve the questions for repeated poles. Let's clear our basics for repeated poles, then we'll solve that question. Okay, so here I have given few poles, basically repeated poles and zeros also. So these are the few examples. Through examples we will understand what happens to my slope of the pole. So like with intuition you can understand that if for one pole we are getting the slope in the magnitude plot as minus 20 dB per decade, for two poles how much slope we will get? We get minus 40. Okay, but let's understand that is that really happening? So let's solve this question for s square, k by s square and k by s cube. So let's solve for the first question. We have to plot the Bode plot for this one. Okay, so what I will do, I will just draw a table here. So here let's first convert this into frequency response format. Then let me bring this more nearer to me. Yeah, that is fine. And this is what? This is k by omega square. Simple k by omega square. Now DC gain of this is infinity. Okay, this gain of this infinity. So we'll draw one table here. Omega. Okay, and this is magnitude of g omega in dBs. Okay, so this will become like, let's find the magnitude for different frequencies. One is for 0.1, 1 and 10. These are all in radian per second. So for 0.1 what is happening? For 0.1 if I want to find the magnitude in dBs, what is happening? Simply do the log 20 log. So here the magnitude in dBs will be 20 log base 10 k minus 20 log base 10 omega square. So this is the magnitude. Now what does this become? This becomes, if I put omega equals to 0.1, omega 0.1 whole square is 10 to the power minus 2. So this is minus 2 comes in front. So this is minus plus 40. This is plus 40. Minus 2 comes in front. So let me just write it. Minus 2 comes in front. So it will be 20 log 10 base k plus 40. You just evaluate for 0.1, you get plus 40 over here. Now you put omega equals to 1 over here. So 20 log 20 log 1 base 10 is 0. 20 log base 10 1 is 0. So this is simply 20 log k only. And if this is 10, then what does this become? So here this is 20 log base 10 square. So this is 2 again comes in front, but this time plus 2 comes in front, not minus 2. So this is minus 40. So here simple calculation I am doing, minus 40. Okay, so this is minus 40. So here I have 3 points, and what I am observing, each decade I am passing, how much I am moving in dB scale? I am moving in 40. So what is my slope? My slope is 40 dB per second, 40 dB per decade. So let's name these 3 points. Like here this is 0.1, this is 1 and this is 10. So here my magnitude was what? Here my magnitude was almost 20 log k plus 40. Then it become minus 40, then it become again minus 40. So this is like a straight line itself. Okay, and what is the slope? slope is minus 40 dB per decade. As we can observe from the calculation itself, that what can we observe from the calculation? We can observe from the calculation itself that it is reducing every decade by 40 dBs. So obviously our slope will decrease like this. Okay, so will decrease like this. But do we know the DC gain of this one? We don't know the DC gain of this one, because DC gain is what? Infinity. Okay, so we'll make this like this. Okay, from point 1 we'll say it is starting. So generally we start our Bode plot from point 1 itself. So you can draw it like this also. Draw it like this also, that it is starting from point 1 itself. Starting from point 1 itself. So at point 1, what is the value? Point 1, what is the magnitude basically? The magnitude is 20 log 10 raised k plus 40. And this is 20 log 10 base k, and this is 20 log 10 20 log k 10 20 log base 10 k, and this is minus 40. If I mess up with the base, right, please try to understand that base is 10 fixed. Okay, so if I even don't even speak about base, it is base is 10 fixed here. So yeah, this is 40, this is 40, so we are moving total like 40 40. Okay, so that's why this is minus 40 dB per decade. So let's like slope formula I'm not giving you. Slope formula we have already done. So for two poles I'm getting slope as minus 40 dB per decade. Now what about for 3 poles? What about for 3 poles? So for 3 poles, how much slope I will get? But before that, one more thing I wanted to tell you is that this is passing on, right? This is passing on. So once it will cross this omega axis as well, and when this will cross the omega axis, let's assume that this is some value greater than 0 dBs. So here we are assuming that this is 0 dB axis, so it will cross the 0 dB axis as well. Can you tell me where will it cross the 0 dB axis? Where will it cross the 0 dB axis? It will cross the 0 dB axis when obviously this value equals to 1. When this value equals to 1, it will cross the 0 dB axis. So here my omega gc will be what? Like my magnitude of g omega at omega equals to omega gc is what? Is simply 1 in absolute terms, not in dB scale, in absolute terms, decimal scale, it is 1. So it is k by s square equals to, okay, not k by s square, k by omega square equals to 1. So omega gc, this is omega gc equals to k by 1 by 2. K by 1 by 2. So omega gc is equals to k by 1 by 2. So this is one of the also formulae. Okay, you can recall from here, or from the Bode plot itself you can understand. From the Bode plot also you can understand that you can solve for here. Okay, like at 1 I have this frequency, so at omega gc, so let's name this as omega gc. From Bode plot also you can do, from mathematically from the transfer function I did it. But if they want to find it, if you want to find it from the Bode plot, how will you find it from the Bode plot? So from the Bode plot, what you will do is that you know the slope formula, right? So this point you will mark this as A, E, and this point you will mark as B. Now what you do is, what is the slope AB? Slope is constant, it is always minus 40. Okay, my slope isn't changing because I have only 2 poles, that all those are origin, and I don't have any other poles or zeros. Slope is always constant. So if my slope is always constant, then what is happening? I know my slope formula, yb minus ya divided by log of omega b by omega a. So omega b is what? Omega gc, and this is what? 1. So this a point is 1 only. This is 1. Okay, and what is yb? Yb is 0 because like unity gain, so 0 dB. and this is 20 log base 10, and this is k. The magnitude at here is k. So this is log of omega gc. This is log of omega gc. So this is log of omega gc. What does this become? Now here this, right? So what is the slope? Slope is minus 40. Slope is minus 40, and this is same only. This is also log base 10. This is also log base 10. Now what is happening? This gets cancelled. So this gets cancelled. So this is 2, and we're remained with omega gc. Like if you divide this by 2, okay, 1 by 2. So this 2 can go here to the power side. I'm doing the reverse property now. Previously I was taking the power outside. Now I'm taking the power inside. So this is k raised to power half. K raised to power half. So from here also you can prove what will be omega gc. From the graph itself also you can understand. Okay, if the transformation isn't given, transformation may not give in always. So from here also you can understand what is my omega gc. Okay, so this 11th one is also simple. Let's do this pretty quickly. Let's solve this 11th one. So again in the 11th question I will just copy this thing, copycat. Okay, simple copycat. Let me copycat this. Just change few things. Here it will become s cube. It will become s cube. This will become omega cube. This will become omega cube. And what will this become? So here if I put 0.1 now, it becomes 0.1 to the power 10 to the power minus 3. So minus 3 comes outside here. So it is minus 3 into minus 20, which is 60. So this becomes 60. Again, right, if you put omega to 1, this again goes vanishes, becomes 0, and this is 20 log base 10k, and this is what? This is minus 60. This is minus 60. Okay, so here we are observing that every decade we are moving in the x-axis omega scale, in the log scale we are moving by 60 decibels, 60 dB. So what will my slope become? My slope will become minus 60 dB per decade. We're moving 60 dB downs. So this is 60, 60, 60. Okay, 60 dB per decade. Obviously from here you can understand that my k this time will become omega gc will become 1 by 3. Okay, we don't need to solve all this. We have already done this previously, so we don't need to solve, waste time here. Okay, so it will become 1 by 3 here, as this omega gc is omega gc cube. Okay, so this will become 1 by 3. So now can we generalize this one? Can we generalize this one? So for this omega to the power n, so here we have this, right? gs equals to k raised to power s to the power n. So what will happen for s to the power n? Just wait, let me check if this is recording or not. Yeah, sorry, there was some error in my iPad actually. So we were here, we're plotting the Bode plot for this one. So what will happen here? Basically, now let's write the generalized expression. So if I write the generalized expression, magnitude of g of g omega equals to like whatever magnitude equals to, in dBs, I'm directly writing in dBs, 20 log k base 10 this is, and minus 20 log base 10 into omega raised to power n. Now this n will obviously come outside, right? This n will obviously come outside. So this n comes outside. Log omega. So this is minus 20n. So this is minus 20n. So here whatever, this is constant value, and this is a slope basically. This is slope. So this 20 is constant here. This 20 is constant. This is just a constant value, right? The k, it shifted up or down. So this is a different component. K is a different component, shifts up or down depending on the sign and all stuff. Sign is obviously positive. It will always shift up. Now depending on like if k is greater than 1 or less than 1. But what does this do? This is a slope basically, depending on the omega. As log 10 omega is varying, this is a slope. So my slope is minus 20 n. Minus 20 n. Okay. Now if my slope is minus 20 n, what does this mean? So basically my Bode plot, gain plot will look something like this. Phase plot is boring because it is constant. Why? Here if you observe, if you write the phase expression for this one, what you will get? Phase expression for this, what will you get? This is k by omega square. Okay. So if you want to write the angle, what do you get? So this is k by minus omega square. So minus is always there. Minus k by omega. So minus is always there. Omega square is real term and k is also real. So obviously we are getting phase always minus 180 degrees. So phase here is constant. Don't be fooled that there will be some slope or something. Don't be fooled like that. Phase is constant, minus 180 degree always. Okay. You replace s equals j omega, you get minus k by omega square. So phase is always minus 180 degrees. Okay. This omega square is real, this k is real, so everything is real. So this is always minus 180 degrees. Here, what is my phase? Can you tell me what is my phase here? Can you tell me? So like basically what is happening? So if 1s is there, this was contributing what? Minus 90. 2s were there, it was contributing minus 180. 3s terms are there. How much it will contribute? Minus 270. Okay. Or you can say plus 90. What you can do is k by j omega whole cube. So this is k by minus j omega. So j can go in the numerator. So it becomes plus j k by omega cube. So plus j means what? Plus j means it is plus 90 plus j. Okay. Plus j is here in the above. Okay. So it is plus 90. So yeah, this is always providing plus 90 degrees of angle. This is boring. Okay. Nothing is changing here. But in the magnitude plot, obviously things are changing. So that is the reason. Be mindful of that. Now what is about this k raised to power s to the power n? K raised to power s to the power n is providing this much. And how much phase is this providing? So I should write the phase also here, side by side. Plus 90 this is providing, or you can say minus, or you can say minus 90 into 3. Here how much phase is this providing? Minus 90 to 2. Now let's understand how much phase is this one providing. This is providing constant phase of minus 90 into n poles are there, so this will provide minus 90 into n phase. Pretty simple. There is no slope, nothing. So let's plot the Bode gain plot. Omega in dBs. Scale is log scale, don't forget. Okay, don't forget. So how will this look? So this will again start from somewhere here, and this will go down something like this. Now what is happening here? So obviously the slope here is minus how much? 20 n dB per decade. Okay, and at point 1 its value will be how much? N times minus 20 n into plus this, right? Minus 20 n plus this, and at 10 the value will be 20 like this minus 20n dBs, and at 1 obviously this will be only the value. Okay, so I will let me just do one thing. Let me write it in short. Plus 20n, this is 20 log 10 base k, and this is 20 log 10 base k minus 20n. Okay, so this is 1, and this is how much? 10. Okay, so 0.1 1 10. So all these things are fine. Again, right, what is omega gc? You can say, what is omega gc? Omega gc will be how much? Omega gc, gain crossover frequency, I can write here itself, equals to simply k raised to power 1 by n. Either you can do it from the graph, or you can do it from the this equation itself. You put this equals to 1, that is my gain crossover frequency. Very simple. Or if you want to do it from the graph, you do it from the slope itself. Okay, slope I have done one method in the first question. So let's now go to the second type of questions where I have zeros present. Now I had poles present, I had zeros present. So slope becomes multiple. How many number of poles are there? It becomes multiplication, multiple of that. Okay, so I have to draw the Bode plot for the following function. Draw the Bode plot for the following function. So let's draw it for the 0. 0 was pretty simple. Okay, let me just so what is this? K into omega square. So again you apply the log formula. So in log terms, log base 10 k plus 40 log base 10 omega. Okay, or you can, yeah, this is 40, for this 40 log base 10 omega. Like 2 will just come in front, right? 2 will just come. You can write like 40 is a slope here. Simple 40 is a slope. Nothing to debate here. What is the slope? So like what is the angle here? Angle this time isn't minus 180 degrees. This time plus 180. Okay, plus 180. Or you can say sorry, this time, sorry, this is how much angle is this? This is oh sorry, this is also minus 180. This is also providing minus 180. Like plus 90 into plus 90 times 2. Okay, that's why this is also minus 90. Minus 180 or 180 is the same thing. So we'll do the angle thing, but first let me plot the Bode plot, gain plot. So the Bode gain plot will be something like this. Like it will rise up. This time the slope is plus 40. Here I forgot to write the slope. Is it? No, write it. The slope. Slope is TB per decade. So this is the slope. Now like these are a few values. I am not interested in the values, but one thing I am interested in is it may start from the bottom itself, right? It may start from the bottom itself. This time what will be my omega gc? So let me assume that it is starting from like below 0 dB axis, starting from below 0 dB axis in whatever frequency. Like let's say starting here 0.1. So what is the value at 0.1? 0.1, the value is 20 log k minus 40. Previously it was plus 40. This is minus 40 now. So the value here is minus 40. Oh no. 20 log k minus 40. Now what is this? This is 20 log k plus 40. Okay, like you can just calculate, like this is at 10, this is at 10, and this is at 1. Okay, so if this is at 0.1110, so now what will happen? Basically, every decade we are moving, it is moving up by 40 dB 40 dBs, right? So now can you tell me, like, okay, so sorry, this is not one, sorry, this is not one actually, I'm really sorry. So one can lie anywhere. Okay, let's say one lies here. We don't know where does one lie, because if my value of k is equals to 1, then only one will lie on the like here where it cuts my 0 dB axis, as 20 log 1 will be 0. Now what is this value? So basically, now what I can say is, let us calculate the omega gc. Omega gc, two ways you can do. Either you can make this equation equals to 1. If you make this equation equals to 1, you can find that k omega gc square equals to 1. So omega gc will be what? K raised to power minus 1 by 2. Okay, because this k is going here, so this is k raised to power minus 1, and we're underrooting both sides, so this is k raised to power minus 1 by 2. Okay, so this is like from the equation itself you can find out, or if you want to find from the graph, how will you find out? Basically, let's do it for here. So let me mark this point B, and let me mark this point as A. So again, okay, let me this time mark this point as A and B. Sorry, A and B. Slope is anyway same, doesn't matter. So what is happening here? Like A point is this one, okay, and B point is this at omega goes to 1. A point is this, okay. Now what is happening? So here, if I write the like equation for the slope, so slope EB equals to YB minus YA. YB is what? YB is 20 log K minus YA is 0 dBs, obviously unity gain frequency or gain crossover frequency, and omega B log 10 omega B minus omega B is 1, and omega is what we have to find out, omega GC. So what is the slope? Slope is plus 20. So 20 equals to log K by, you can write here minus 1, okay, because this 1 by omega GC. So if I just want to take the inverse of this one, I can write here minus log 10 of omega GC. Now this one will become okay, this 20 got cut out, so 20 got cancelled, right? 20 was slope. Okay, let me just 20 and 20, this 20 gets cancelled, so we're left with log of 10, and I can bring this minus 1 to this side, multiply minus 1 to on both sides, and again this minus 1 and I can take inside. This will be log of 10 k raised to power minus 1. So omega GC, okay, sorry, the slope is plus 40, sorry, the slope is plus 40, which is going in a hurry. Here it is 2, so here it becomes, let me now write it better manner, this becomes minus 1 by 2. So omega GC is simply equals to k raised to power minus 1 by 2, because the power goes inside, right? power goes inside like this. So this is what my omega gc is. So like you can find out from here also, from the graph also, from the equation also, like both ways you can do. I have not explained it much further. Let's now come to the generalized case where g of s equals to k raised to power n. So if g of s equals to k raised to power n, what will happen? Simply my magnitude function. Okay, I forgot to talk about the phase. So what is happening to the phase? Here if I see that simply angle of g of j omega will be how much? So this is always positive. This is always positive. So how much angle I'm getting? I'm getting one simply 0 degrees, right? Sorry, not 0. Sorry, minus like this is always positive, but like when I'm putting s equals to like j omega, what is this? So j omega equals to k j omega whole square. So this is how much? This is minus k omega square. So obviously minus is there. So obviously we're getting 180 degree angle, either plus 180 or minus 180, it doesn't matter. But I will just write it in terms like this, that it will be plus 90 times n. Plus 90 times n. Okay, so plus 90 times n is also like plus 90 times 2 is also 180, which is again like you can say minus 180 also. Now let's do it, solve it for this one. That what does this become? This becomes like the magnitude of g of j omega will be k raised to power n, k raised to k into omega raised to power n. And what will my phase? So phase will be plus 90 times n. Okay, simply as this is in the numerator, previously my omega was in denominator, it was minus 90 times n. Okay, this is very simple, not that difficult to understand. So now let's do one thing. Let's like write it in terms of dB scale. So if I write it in terms of dB scale, what will this become? 20 log base 10k plus 20 n log base 10 omega. Okay, so this is this case. So how is the slope becomes plus 20 n? Slope becomes plus 20 n. So this is the slope. So if I just draw the like Bode plot, I won't explain it much further. It will be like this. It may cross the 0 dB axis. Okay, like sometimes this may be the 0 dB, or this also can be 0 dB. They won't mention you that this is always the 0 dB. It isn't important. It isn't like important that this will be only 0 dB. This can be anything. Can be minus 100 dB is also this axis. Okay, so I'm just telling you, yeah, wherever it cuts, for easier visualization, that yeah, this is 0 dB. It may so happen that this is not 0 dB. So yeah, that is one thing I want to mention. The slope is here plus 20 times n dB per decade. Okay, this is magnitude of g of j omega. This is omega. Okay, so this is the case. Now now let's do one thing, is that what else we have to do? What else we have to do? So this is the case. Okay, what else? I'm just suffering. Okay, yeah, the omega gc. What is the omega gc? Omega gc was simply k raised to power 1 by minus 1 by n. Minus 1 by n. This time it was plus 1 by n. That time it is minus 1. Simply it's the reverse. Right? If you put this in this equation also, you will get. Okay, if you don't want to put this in equation, you use the graph slope method, you will get whatever you want to do, you do. So these things. So obviously I have summarized all these things here. Okay, don't worry, I have summarized all these things. So what is the conclusion? Conclusion is I'm talking about the Bode magnitude plot. Okay, for the Bode phase plot, the phase is simply here. I haven't have I written no. I will write the phase. Okay, the phase In this case, omega g will be simply minus 90 degree times n. It will be constant. That is very important. People get confused from this. This is constant. And here my phase is plus 90 times n. Okay, so here also this is constant, not changing. Okay, so this is the case. So this is the omega gc, this is the omega gc for this, like when you have k bias to the part. And you can see now one more thing to note here is that omega gc will be greater than 1 when my k is greater than 1. Why? If my k is greater than 1, obviously whatever the under root we take, right, it will be always greater than 1. So this is the case. And from here also you can understand, like you just put something k equals to 0.1. If you put k equals to 0.1, this becomes even lower. Okay, hence this is less than 1 always. If you put k equals to 2, what does it become? It will always be higher than 1. It can never be lesser than 1. So under root 2 is something 1.414. Under root, you can do under root 1.01. It will be always more than 1, because 1 square is 1 itself. Okay, so that's why. So anything less than 1, it will, the omega gc will be lie lower than the 1 radian per second. Anything more than 1, it will lie more. The gain crossover frequency will lie more than 1 radian per second. And for this zero case, in repeated zeros, it will be just the pure opposite. Okay, so these are the things that I wanted to tell you about this Bode Bode magnitude plot for repeated poles. Now let's solve that homework question what I gave you. So what was the homework question? If I can find it somewhere. Can I find it somewhere? Yes, I can. Yes, here. Now from the conclusion we can solve. Let's first convert this into normal time constant format. So general time constant format, I will convert this. S plus 1 divided by 2 square into S plus 2. Oh, sorry, I'm taking 2 common. Okay, so now, okay, 3 is also common, so this will be 3. And how much is it in the bottom? How much is it? So in the bottom, this is simply some 1 divided by 12 into S plus 2 by 1 into S plus 3 by 1. Okay, this is my G of S. Okay, so now can you plot the Bode plot for this one? So sorry, this is square also. Sorry, one thing to note here is that like what is happening to the slope? Due to this one, I'm getting minus 40 dB per decade. As I told, right, if I have 2 repeated poles, I will get minus 40 dB per decade. Now, like here, there you might say, sir, it was at origin, but this is not at origin. For origin, the slope will change. No, slope won't change. If you want to like understand this, so let's only write the magnitude for this one. So if I only write the magnitude for this one, what will this become? This is the denominator. Obviously minus 20 will come. Minus 20 log 10 omega by 2 whole square plus 1. Okay, now how do we calculate the slope? Basically, and also there is a square also, so this will also be a square. Okay, hence this 2 will come outside, so this will become minus 40 log base 10, whatever this is inside. So whatever slope I was getting for a single pole, okay, this will become twice, simply twice, right? So this is minus 40. So very simple, so like, I hope you understand. Now I won't write the table now, okay, where we are slowly becoming accomplished that we don't need to draw the table for this Bode magnitude plot. For phase plot we may need to, for Bode magnitude you don't need to, you can do this directly. How to do this directly? That's why Bode plot is so convenient. So first, what is my DC gain? DC gain is, let's say, I'm naming it some variable m equals to 20 log base 10 1 by 12. This is some variable. I don't care about this one, so I'm not calculating this. So this is my magnitude of g of j omega in dBs, and this in omegas. So now what is happening? Now like this is some value m, okay, and we are starting from point 1. So as we can observe, as most of the poles are not nearer point 1, right? So we can assume that like DC gain is m also. We can assume that because point 1 is ignored everywhere. So if you put point 1 here, it will be almost equals to 20 log 1 by 12 almost, if you put point 1 in this equation or in the magnitude equation. Okay, what I should do is, yeah, now at where am I getting poles? So let me just write the corner frequencies. So first, what is the lower corner frequency? S equals to 1. So S equals to 1, and then S equals to 2, then S equals to 3. These are my corner frequencies, 3 corner frequencies I have. Now like first I am getting a 0, so first it will have a slope of plus 20 dB per decade. This is how you do this directly. Okay, in examination obviously plotting won't come, actually mainly the reverse will come. The plot will be given, but you have to find out the transfer function or something, some parameter or something. But if you don't understand the plot itself, then you won't be able to do the reverse thing. First we are doing this plot, then we will do the reverse thing. Then okay, now we have a 0 at this corner frequency, slope is plus 20 dB per decade. Now what is happening here, the slope becomes like I have an addition of minus 40 dB per decade slope. Also I had initially plus 20 dB per decade slope. So overall how much slope do I have? I have plus 20 minus 40, which is minus 20 dB per decade slope. So overall I have minus 20 dB per decade slope. Okay, so this is minus 20 dB per decade slope. Now what is happening? Now at 3 my slope is becoming, again an additional pole is getting added, so an additional minus 20 dB per decade slope will get added. So my slope will further reduce, and it will like the function will reduce very fast. So here what is my slope? Here like before this corner frequency, my slope is 0 dB per decade, and here my slope is plus 20 dB per decade, and here my slope is minus 20 dB per decade, and here my slope is minus 40 dB per decade. Okay, so these are the slopes, like that's how we understand. Okay, like I told you, right? I told you that what we can do. So the slopes is getting minus 40, I told you in rough. Now what is happening to the angle? What is happening to the angle also? So if you want to write the angle expression, just the angle expression for this one, I'm writing the angle expression for this one, other ones I am not writing. So what is happening here? So you have two poles at that equation, right? So what you will get, so due to one of them, it will be tan inverse omega by 2 by 1 pole. then another pole, so obviously that phase also is there, right? So that algebraic sum simple, tan inverse omega by 2 by 1 again. So I'm just doing this enough. So this becomes 2 tan inverse omega by 2, hence slope is doubled. So let me just okay, let me do one thing. Let me do this in fair way because people will read this. Let me write the angle equation anyways. So angle equation will be due to the 0 tan inverse omega. Now due to the poles, what is happening? Tan inverse, due to this one I'm getting two poles, right? So it will be 2 times tan inverse omega by 2 plus tan inverse omega by 3. Okay, so obviously what is happening here, that my slope is getting doubled. My slope is getting doubled. So this is the case. Now let's plot the Bode phase plot. So yeah, this is a bit difficult, but still we'll do this. This will be time consuming, so what I will do is I will copy that previous table. So let me just copy this table. Where is the table? Yeah, here is the table. So slope of values. So what are my important frequencies here? So obviously my important frequencies are 0.1 to 10. Okay, so I have a 0 at 0.1 to 10. So 0 at 0.1 to 10, not this one. So 0 at 0.1 to 10. And what about my pole? I have poles from 0.2 to, like the effect I'm talking about, effects 0.2 to 20 and 0.3 to 30. I'm not talking about exact location of pole, but the effects of the pole and zeros. It will be 10 times before and 10 times after. Yeah, this is fine. So these ranges are fine. These ranges are fine, but these are not fine. This will change now. So before 0.1, obviously nothing is there. So 0 degrees. Now after 0.1, what do I have? I have a 0. So now this effect isn't coming between 0.2. So this will come after 0.2 and this will also come after 0.3. So after 0.1, only this is coming. So obviously this will be plus 45 degree per decade. Plus 45 degree per decade. And here, right, I have to tell here this has to be multiplied by 2, as I have 2 here. As I have 2 here, so this has to be multiplied by 2. Okay, effect will be twice. Okay, just highlight this one. Now from 0.2 to 0.3, 0.2, the effect of these two poles are coming and the effect of this is also present, but this is still not present. So obviously what is this slope providing? What is this 2 pole slope providing? These are providing me minus 90 degree per decade. One pole minus 45, another pole at the same location provides me another minus 45. So overall I am getting minus 90 dB per decade. So overall I am getting minus 90 dB per decade and this is providing plus 45 degree per decade. So overall what I am getting? I am getting minus 45 degree per decade. So here my slope is minus 45 degree per decade. This is 2 times pole and 1 0. And after this, what is happening? This 0.3, this 0 is all, this pole is also coming into effect. Another minus 45 degree per decade will get added in this slope. So minus 45, another gets added. This becomes minus 90 dB per decade. So this becomes minus 90 dB per decade. So here this is twice. And what after this, what is happening? Obviously the effect of this after this 10, the effect of this 0 is also gone. So it was providing plus 45 degree per decade. Now it is gone. So now another 45 degree will get subtracted from here. The effect of this one is gone. So overall I have minus 135 degree per decade slope here. So the slope becomes 135 degree per decade. I have two poles. Okay, after this obviously the effect of this pole is gone. After 20 the effect of these two poles are gone, so another plus 90 will get added, like plus 90 will get added because I was subtracting 90. That extra 90 I don't need to subtract anymore, so this will get reduced to 90. So this is fine, this is 45. Then after this 30, obviously the effect of this is also gone, so I am going to 0 again. So this is my distribution of slope between each points. Okay, now let's plot the Bode phase plot. So the Bode phase plot, so like let's start from point 1. Okay, point 1. So before point 1 it is constant, obviously. Let me use another color. Point 1 it is constant. Now after point 1 what is happening? After point 1 I am getting plus 45 degree per decade slope. So this, okay, let me just mark the points first. Let me not mark the points because it becomes difficult. So plus 45 degree per decade slope. Okay, pretty low, so I will make this scale pretty low. Plus 45 degree per decade slope. Then after this my slope is changed to minus 45 degree per decade slope. So if it was 0 degree it would have been like this flat. Now it is minus 45 degree, so this will be like this. Okay, now after this what is happening? My slope is again further reducing to minus 90 degree per decade slope. So it will become minus 90 degree per decade slope. Then what is happening? Then it is becoming minus 135 degree per decade slope. So I will not show this reduction this much. I will show this because it is so lesser also. So this will, let's bring this to more top. So this is minus 135, and after this what is happening? It is increasing now. It is going to minus 45. So again this becomes minus 145, sorry 45. Then after this it goes to 0. Okay, so this one is 0 degrees per decade. This is plus 45 degrees per decade, and this is how much? This is minus 45 degrees per decade. This is minus 135 degrees. Oh, not 135. This is minus 90 degrees per decade. This is minus 135 degrees per decade. This is again minus 45 degrees per decade. The effect of two poles are gone, and this is 0 degrees per decade. Okay, now let me write the corner frequencies because it is difficult for me to exactly like write all the corner frequencies here. If you see, this is 0.1, this is 0.2, 0.3, 1, 2 and 3. So 0.2, 0.3, 1, 2, 3, like this. So yeah, these are like this. Sorry, this is, yeah, 1, 2, 3, fine. Okay, sorry, one thing I made a mistake here. Sorry, this is 0.1, 0.2, 0.3, that is fine. Now this is not 1, this is 10, 20 and 3. 10, 20 and 3. So from Bode phase plot, it is actually pretty difficult to find the like the transfer function, like recover the transfer function. Like here, these don't represent, like the wherever the slope changes, they don't represent my corner frequency. They represent 10 times less corner frequency and 10 times more corner frequency. So as this is 0.1, so 10 times more than this is 1, so that is my corner frequency. This is 0.2, 10 times more than this is 2, that is my corner frequency. 0.3, 10 times more than this is 3, that is my corner frequency. 10 is here, so 10 times less than this is 1, which is corner frequency. 20 is here, 10 times less than this is 2, which is corner frequency. 30 is here, 10 times less than this is 3, which is my corner frequency. So we'll recover the transfer function from the Bode phase plot. From there we'll understand how to recover the transfer function from the Bode phase plot itself. Okay, for now just understand how to plot the Bode phase plot. It is difficult to plot the Bode phase plot also. Another thing, where will this end? Where will this like phase plot go? That we can tell. Where it will end to minus 180. Why? Because number of poles I have 3, number of zeros I have 1. So ending, I told you right in the short notes, like in the key points, that it is minus 90 into n minus m. So obviously minus 90 into 3 minus 2, which is 3 minus 1, which is minus 180. So this is minus 180. Minus 180. Okay. So this is minus 180. Now what is happening? Now about this also, about the ending slope of this. What is the ending slope of this? Minus 40. Here also from formula you can calibrate that it is minus 20 into n minus m. So minus 20 into 3 minus 1, which is 3 minus into 2, which is minus 22, is minus 40 dB per decade. Okay. So these are the things. So yeah, so this is basically about this one. So here I have given you the summary of repeated poles, what is happening to the slope, what is happening to the poles, all these things I have given you the summary of. So let me just use some different color for this. Let me write this in a better manner. Okay, this is bring this down. Let me write this in a better manner. Actually, slope becomes, when I have repeated poles, the slope becomes how much? Slope becomes n times of that basically. Slope becomes minus 45 degree n, basically minus 45 times n degree per decade. Okay, so what happens to the slope here? Here the slope becomes, okay, the color should be different actually. Becomes plus 20 m dB per decade. Here the slope becomes plus 90, not 90, sorry, plus 45 m degree per decade. So this is the slope here, and this is the slope here. Okay, so yeah, these are the things that I want to tell you, summarize. So these are few questions you can do, and this question I will do in the next class. I'm giving you the homework for these two questions, simple only, repeated folds. Okay, I'll just draw them and just show you in short how to do this very fast, how to plot the Bode plots very fast, as I plotted the Bode magnitude plot in this question. So magnitude plot you have to do. Okay, and in the next class we will understand about the error in the Bode plots, and also the Bode plots for second order systems, standard second order systems. Okay, also we'll understand the recovery of transfer function of Bode plots from the Bode plots. Okay, then we'll do few questions, like that will be one lecture after that. So next lecture will also be theory. Here we have done few questions, but next lecture will also be theory. After that we'll do questions. So yeah, thank you for watching, and I will see you in the next lecture.